professor for theoretical physics in Kassel, and I'm working on atomic, molecular, and optical physics and quantum information science, so a broad range of applications. And the common theme is, you will be surprised, quantum optimal control. And with this, I hand over to Thierry, who is another PI from the network. So Thierry, can you introduce yourself briefly? Okay, I don't hear anything from Thierry. Then I suggest Elke, you say something.
Yeah, okay, can you hear me?
Yes.
Okay, thanks. Yeah, so my name is Elke Neu. I'm junior research group leader at Saarland University. And we are working indeed on NV centers. We are trying to use the NV centers as nanoscale sensors. And within the project QuSCo, we have actually been starting new in the field of optimal control. So we indeed hope to profit a lot from the network. To whom shall I hand over?
Maybe you can hear me now?
Yes.
Hello,
yes.
Christiana?
Yes,
okay, good. So I've unmuted my phone because I'm waiting for the bus just now, so I'm outside. Okay, so I'm Thierry Debucher. I'm working in Thales, a company, so close to Paris. And my main subject is NV centers in order to build or to new sensors. And we are mostly interested in ensembles of NV centers, and that's why coherent control can be interesting in order to improve the properties of those ensembles of NV centers. And I'm the advisor of Simone Magaletti, who is online. Okay. Can you hear me?
Yes, so thank you, Thierry. And then maybe to make things easier, let's now go through the list as it shows up on your participants on the QuSCo screen. So Mattia, I suggest that you also say a few words and then hand over to Alistair.
So I am Mattia Giardini. I am the project manager for the project QuSCo. I work with Christiane at the University of Kassel. Previously, I collaborated with Tommaso Calarco in the effort to establish the quantum technology flagship, and I look forward for the success of this project. So let's move on to the next person, which on my list is Alistair and Fila.
Do you want to go?
Sure. Hey, no, we are unmuted. So I'm Fila Rembert. I work at Ulm at the moment, but my supervisors are Tommaso Calarco and Simone Montangero. So actually, next month I'm doing my secondment with Elke Neu and Nimba, and then afterwards I'm gonna go to Jülich and work there with Tommaso Calarco. I work on optimal control of NV centers, specifically with DCRAB and RedCRAB. Yeah.
I'm Alistair Marshall. I'm working for NVision during my PhD, and I'm looking at optimal control of NV centers as well from a more experimental side, but also encompassing theory in whatever way possible.
So with you there is also Philip, right? So maybe a few words from Philip would be great.
Hi, my name is Philipp Neumann. I'm also part of Envision Imaging, and yeah, as I have some experience in optimal control, I'm also helping Alistair, learning from Fila and all the others.
Okay, so the next on my list is Andrea Muni from CNRS, I guess.
Hello, everybody. My name is Andrea Muni, and I work as PhD student in the group of Sebastian Gleis, Michel Brune. What we do here is atomic physics. So we do electrometry, magnetometry, in some sense quantum control and sensing on the rubidium atom.
Okay. The next on my list is Emanuele Albertinale.
Can you hear me?
Yes, it's clear.
So, hi everybody. I'm Emanuele Albertinale. I work in the group of Patrice Berthet at Saclay near Paris. And we mainly work with NV center or bismuth donors coupled to superconducting circuits.
So that is Eugenio Pozzoli.
Yeah, hi everybody. Can you hear me? Okay, I guess so. I'm Eugenio Pozzoli, and I work with INRIA in the Team Cage in Paris with Mario Sigalotti and Ugo Boscain. And now we are working on basically on controls of quantum systems of rotating molecules. And the aim is to find controllability properties of the dynamics, looking in particular at the quantum angular momentum by means of electric fields and using potential the Stark effect. And for example, from linear molecular, we are passing through symmetric and asymmetric top, and we're working on that.
So the next will be Federico Roy. Please unmute yourself.
Can you hear me?
Yes.
Yes, okay. So I'm Federico. I'm a PhD student working in collaboration between University of Saarland and IBM Zurich. I'm working with Shai and Frank at University of Saarland and Stefan, Philip and Max Werninghaus at IBM. We're going to try and do optimal control superconductive qubits. And that's the main aim.
Thanks a lot. The next person is Fernando Gago.
Yes, hi everybody. My name is Fernando and I'm a PhD student at university under the supervision of Christiane. Right now I'm working on optimal control theory on Rydberg atoms, especially trying to apply the superposition state designed for a magnetometer. So I also look forward with the segment I will have to do in Paris for that.
So the next one is Jesper, which I guess is one of the students that asked through Frank to be connected. Can you hear us, Jesper? I see. Jesper has no microphone, so and he's from the group of Jacob. So let's move on to the next, which is Marwa Garci.
Hi everybody, so my name is Marwa Garci and I'm a PhD student in the group of Professor Warthoop, where we are working with NV centers, and in my case it's a bit similar to Thierry, and I'm working with ensemble of NVs, where here optimal control can be used to homogeneous control of the NVs. That's all for me.
Thank you. The next is Max and Stefan, if he's still connected.
Yes, we are. Hi, my name is Max Werninghaus. I'm working with Stefan Philipp and Daniel Egger at IBM Research Zurich on superconducting qubits, and we are closely collaborating with the theory group of Frank Wilhelm Mauch in Saarland University. Our goal is to do optimal control to control single and multiple qubit gates.
So let's move to Nimba.
Yeah, am I audible?
Yes, yes.
Yeah, so I'm Nimba Oshnik. I'm working at the Saarland University in the group of Elkenau, and we are working with optimal control for sensing with these scanning diamond probes.
Yeah. Thank you. The next one is Shima from the group of.
Yes, hello?
Hello.
Yes, hi, I'm Shaima. I'm from the group in Aarhus University. I'm doing my PhD under Jacob Hirsen, and my sort of main focus in the QuSCo project is how can we build gamified interfaces to combine many body quantum control problems and the control algorithms, and how the way in which both of these can be visualized and placed within an interface. Yes, thank you.
Thank you. The next one is Simone Magaletti. I'll keep Shai for later, so it will be the last one. Simone, can you unmute yourself and present yourself?
Yes, can you hear me?
Yes, clear.
Okay, I am Simone. I'm with Ludovic. We are working with Thierry. As he already mentioned, we are working on NV ensembles. So the idea is to use optimal control to improve our sensor.
Thank you very much. The next on the list is Stefan Glaser and Amit from Munich.
Hi, I'm Stefan. We are here at the university, at the Technical University in Munich. My focus is on optimal control of finite dimensional quantum systems, in particular experimentally. We also look at NMR experiments using spins. And we're also interested in visualization and gamification of such quantum control experiments. And I'm supervisor of Amit.
Hi, it's Amit Devra, and I'm working as a PhD student in DUM under the supervision of Stefan, and I'm also working in the same field, quantum control, and we are working on using NMR quantum information processor for all these processes and for the visualization of spins as well, and some tomography things of that.
Thank you very much. The next person is Tian from Wien, I guess.
Yes. Hi.
Hi.
Hey everybody, so my name is Tian, and I am a PhD student in Jörg Schmidt-Meyer's group at TU Wien in Vienna. So what we have here is that we are working on one called CBC with iridium, we're trapping it magnetically using atom chip. Then we have like in our experiments, we have had a long history of working with like sequences generated using like especially GRAPE from tomosyntheticals, like to manipulate the motional states of RBC to do like RAMC interferometers, and nowadays also like double twin beam experiments. And that's like so far. So I guess that's all the updates from outside. Thanks.
Then the last person on the list I see is Tobias Stollenberg. Would you please introduce yourself? So I see you are unmuted, but I can't hear you. Okay, well, since unfortunately I can't hear Tobias, I think we can now move on to Shai, who can then also present himself and start with the lecture, I think. Christiane, would you like to add anything later?
Actually, I think it will be fair to ask to not have the chairman introduce himself. So first of all, everybody who's not Shai, please turn off your video, because it will reduce the bandwidth that we need. And then everybody will be able to see Shai. And so I'm very happy that Shai has agreed to give this first QuSCo on Error lecture. Shai is currently a senior postdoc with Frank Wilhelm, but has been using optimal control, if I recall correctly, back to his PhD days or very junior postdoc days, and he has worked on various quantum information platforms, from ions to photons to superconducting qubits. And if I'm missing something on this list, I think it's not too bad, because you'll probably hear a few applications also in this talk, but the focus today will be on method development or method fundamentals, and this is also a focus of Shai's work. And Shai is not only a theoretical physicist, but also a developer of algorithms, and you may have heard of the Dynamo package, which is a ready-to-use software package that Shai has initiated and coordinated. And so he has really the expertise to start this first lecture. And again, I remind everybody, feel free to interrupt Shai whenever you have a question. And we're looking forward to your lecture. Shai, please, stage is yours.
Hi, everybody. I'm Shai, as everybody mentioned. I agree, feel free to interrupt if there are questions. There are on this talk at least 3 people more knowledgeable than I in optimal control, so if I make any mistake, I'm sure they'll jump in and correct me. And let's go. Okay, I'll share my screen. Just let me know if you can see the share. And here we go. Can you see the screen?
Yes.
Somebody say yes? Okay. All right. Okay. So what I'm going to do is give a review of quantum optimal control as much as can be done within the time we have. The 2 first references you see on screen are kind of general overviews. And there is one thing I do have to mention. Everybody giving a talk on quantum optimal control tends to do this from his own little corner of the world. So, for example, there's the GRAPE optimal control method coming from Stefan Glaser. There's the Krotov optimal control method, which Christiana is leading. I have my approach, which is GOAT. So take into account that every presentation will be slightly skewed towards the presenter. Okay, so what will we do? We'll talk about optimal control in general. I'll present some of the more common algorithm used in this area. Then I'll talk about what we're looking for in a good optimal control method. I'll present the optimal control method which I developed, which we call GOAT. Then we'll cover some issues regarding quantum optimal control in general, such as controllability, local traps, stuff like that. And we'll talk about where are we going with this into the future. So let's start with what is optimal control. Well, this, right? Everybody does this, and we save, half a second by cutting off the corner and destroying the lawn. This is actually a kind of very accurate depiction of what's going on, because there are kind of trivial solutions to the problem, but often they are suboptimal. And by tweaking the solution or sometimes changing it in a major way, we get to a far better solution. Now, one of the uses of optimal control before quantum is in space travel. So let's say I have the Cassini-Huygens probe and I want to reach Saturn, but our rockets aren't very powerful, so I need to do it with a minimal amount of fuel. So how do we do it? Well, this is the actual trajectory of the Cassini-Huygens probe. And you can see that it left Earth in 97 and then got a gravity assist from Venus and a second gravity assist from Venus, and somebody's not muted, so if you could, please. And then another gravity assist from from Earth, Jupiter, and then on to Saturn. Now, to calculate this kind of trajectory by hand is impossible, and therefore you need numerical methods to assist. Another point that's interesting to note is that, for example, if you consider the gravity assist around Jupiter, the idea is that you come behind Jupiter, you steal a little bit of its of its energy, of its angular momentum as related to the sun, and that pushes you forward. Now, doing this assist requires that you are already close to Jupiter. Because if my trajectory is traveling very far away from Jupiter and I'm trying to compute how to change the trajectory, I won't feel Jupiter at all. And the idea that you need to be in the neighborhood in order to see the gradient of how to improve your trajectory, this is something we'll run into with quantum systems as well. Okay, now this, can you see the movie?
Yes.
Okay. You can see here, this is a waiter race from 1949. And if you notice how they tilt the tray just before they start moving so that the glasses don't fall off. This is another example of optimal control for a dynamical system where you need to do a preparatory step before you start the process. And we'll see that as well. Now let's go to the quantum system. Okay, so what is the problem? We have a Hamiltonian. The Hamiltonian contains a drift term, which is H0, and a number of control Hamiltonians, which are Hk, and a control fields that determine how strong, how powerful is this control Hamiltonian. Now we have control over C of t to some degree. I mean, we can't do anything we want. We're limited in bandwidth, we're limited in power, but we can determine the shape of these functions. So our goal is to find the control fields, Ck, such that we generate the desired dynamics. This can be quantum gates or a state transfer or state generation, and we want to do this accurately, we want to do it fast, we want to do it robustly in case there is noise in the system, which usually there is. So that's our goal. From a bit more formal perspective, let's define our goal function, G. We have a goal unitary, U goal, and we have the unitary we actually implement, which is U at final time t. Okay, the vector alpha here, that's the parameters of our pulse. Now what you have here is you have the infidelity. So you're looking at the overlap of U and U goal, right? If U is equal to U goal, then U dagger U will be the identity, and then you do the trace and 1 over the dimension, and you essentially get a G0. But if U is not equal to U goal, then G will be greater than 0. So our purpose is to find alpha to minimize G. Now what is U? What is the unitary we're implementing? Well, this is just the time-ordered integral over the Schrödinger equation. By the way, can you see my cursor?
Yes.
Okay, thank you. Okay, so this is the time-ordered integral over the Schrödinger equation, which is the stuff we're used to, nothing special here. And h of alpha is, as we mentioned earlier. Now let's be explicit and give an example. So in this case, we'll say that our control pulses is made up of a collection of Gaussian pulses. Okay, so the control field is a collection of Gaussian pulses, and the vector alpha is just the amplitudes, the center times, and the width of these Gaussian pulses. And of course, we will have constraints on the system. For example, we can limit the amplitude of the pulse. And our goal is to find the vector alpha such that G alpha is minimal. Okay, so from a mathematical perspective, this is a well-defined problem. Of course, this is a specific example of a gate generation where you want to generate a certain unitary U, let's say a C0 gate, but more generally, this can be an open system. There are a million variants. Okay, so how is this optimal control stuff used? Okay, so this is kind of generally known as the ad hoc protocol. And the idea is fairly simple. You design a system, you fabricate the system, you characterize the system, you measure the frequencies, the coupling, whatever it is you want. You then have a model of the system. You put that into an optimal control package. You design a control pulse. and then you put it into the system and measure the fidelity of the pulses, right? So you measure G in practice in the experiment. Now, often this doesn't work as well as you hope, so you start tweaking the pulse, and this is a closed loop optimal control process where we improve the pulse shape until it actually works well. Now, a few more statements. The fact that you need to calibrate the pulse is essentially an indication that our model is not perfect, but this is almost always the case. Okay. For example, if I'm thinking of, let's say, superconducting qubits, and your control pulses are in the gigahertz range, right? So microwave pulses, you have some frequency-dependent attenuation on the line, but we often don't measure and don't know this exactly. So our model is incomplete. Okay, a few more comments. When we measure the fidelity, there's a long discussion about what's the right figure of merit. How do you know when your gate is good? And I won't go into the discussion, but it's worth realizing that this is a non-trivial point. Another issue is how do you adjust the pulse? So when you calibrate, we are essentially doing a gradient-free search. I'll talk about it later. I've seen a lot of experimental groups use Neldermead. That is problematic for several reasons, and we recommend people use other methods. Okay, now let's talk about the quantum optimal control algorithms out there. Generally, one can divide them into two categories: gradient-free optimization and gradient-based optimization. So in direct methods or gradient-free, there is no gradient information, meaning you evaluate a point and that's all you know about the system. Okay, so now let's look at a direct method. It's basically a black box optimization. So you evaluate your several proposed control pulses, which translate to several possible values of the vector alpha. And then you kind of think about it a little bit, decide on a new set of points to sample, and repeat. The little triangle walking on the landscape you see in the plot is a typical Neldermead optimization. Oh, sorry about that. Is a typical Neldermead optimization where you have, let's say, for a case of a 3D surface, 2D surface, you have 3 points, and you always look at what's the lowest, the highest point, and reflect it through the triangle, and this is how you proceed. Now, the good things about gradient-free optimization is, first and foremost, it does not require the gradient information. When we're talking about calibration, in the context of an experiment, we simply don't have the gradient information, right? Only thing we can do is evaluate a pulse and see how well our system responds. So that's the primary reason to use gradient-free information. Another is that there are certain types of numeric simulations, such as tensor networks, where the gradient information is not easily available. So I can simulate the system, but I can't figure out with ease what is the gradient of the fidelity with respect to the control parameters. So then in that case, it will also make sense to use a gradient-free optimization. And of course, gradient-free optimization is very simple, right? But however, there are reasons to avoid it when possible. The primary reason is that it's slow. And if you go to systems where your vector alpha has, let's say, 10 or more parameters, then gradient-free optimization tends to become very slow. And I'll give an example here. I think in this case, we optimized a 2-qubit CNOT gate for the X1 system, such as used by Google. And the goal function on the y-axis is actually the log of the infidelity. And what you see is that the blue line is the GOAT algorithm, which I'll present later, but this is typical of gradient-based optimization. And the red line you see is a simplex search, or in other words, Nelder-Mead. And you can see that Nelder-Mead is many orders of magnitude slower than gradient-based algorithms. So for calibration, we have no choice.
Sorry, do you mind if I ask a question?
Of course.
Yes. So I was wondering, this is also similar to the graph in the paper that you put on the Dropbox. Yes. And now this time in minutes, how do the iterations, for example, compare? How long they take? Is this time in minutes on
so this
cluster? Is there something parallelized?
No. So this is a
comparable. How's it comparable?
Okay, so this is basically on my laptop, and a propagation, like a system propagation, takes well under a second.
Okay, so the iterations of GOAT are still faster than the iterations of the simplex search. Is that correct?
Yes, and that's typical. I mean, here it says GOAT, but I think for the purpose of this stage in the talk, you can think of it as any gradient-based optimization method. So having a gradient is hugely helpful. And in case of, let's say, a CNOT gate on an X1 system, if you do a proper simulation of the system with multiple energy levels, the resultant pulse is not super simple. There are quite a few parameters to optimize. And in this case, Nelder-Mead in particular has a really hard time with this. This is especially true if you get to regions of the parameter space where they're relatively flat, meaning that you get a very weak response, a very small change in the fidelity as you change the pulse parameters, right? And if you kind of go through the experience of running optimal control algorithms, you'll see they often progress in stages, meaning they make some progress and then they get stuck for a while, and then they make progress and then they get stuck for a while. The getting stuck is that they're essentially in some saddle on the landscape of control parameters, and they're searching for a way out of this plateau. And in that case, having a gradient, knowing how far one should walk, is extremely helpful. Another comment I want to make in this context is that people sometimes feel that, well, if I don't have a gradient, I can make a gradient by doing finite differences and evaluating close points in parameter space. But if that is the case, it is always preferable to use gradient-based search methods. The reason is that, I'll phrase it like this, use gradient-based search methods when it's much cheaper to get the gradient than to do finite differences. If the only way to do to get the gradient is finite differences, then using gradient-based is not worth the effort, because you can learn after every point you evaluate using more sophisticated methods. Okay, now let's go on to CRAB. CRAB is combines two ideas. One is that you take a random basis, usually a Fourier basis of functions. You set this as your ansatz, and then you do a Nelder-Mead search over these parameters. Now, of course, one can replace your Nelder-Mead with more sophisticated methods, such as CMAES and others. This method is deterministic, and it works surprisingly well. I think one thing one can learn from the CRAB method, and there are variations to it. For example, if the parameter space is very large, and let's say Neldermead has trouble, one can switch between various subspaces. So you freeze some parameters, you do a search on a subset of parameters, then you freeze another set, and you do a search in that direction, etc. What it has taught us that often just choosing random base function works, which is a very positive message. It means that quantum optimal control is not that hard of a problem. You don't have to find this one particular unique pulse that can only be described in this very special basis. You can take any, take 20 random Fourier components. If they are in the rough neighborhood, it'll work. Okay. For example, for tensor network calculations, this is a very good method. Now, there are also stochastic methods. CMAS is a very popular one. Basically, you start with a cloud of points, then you evaluate the goal function for a set of pulses. You learn something about where to go, and you update your cloud of points. And this is kind of progresses like this. This is a very easy method to use. There are almost no meta parameters to kind of to set up. There are a million open source implementations. So if you have gradient-free search, I highly recommend using this. It's also fairly robust to noise. It may not be the latest and greatest search method, but it is very, very good, and it's very easy to use. There are, of course, other methods, such as simulated annealing, and there are genetic algorithms, etc., etc. So this area of, let's say, gradient-free search is a very active research area in computer science. There are conferences dedicated to it, and I think the quantum context doesn't really add a lot here. It just happens to be a search over a quantum system. But we just need to kind of pay attention to what the people in computer science are doing. Okay. Now we'll talk about variational methods. So variation methods are gradient-based, meaning I assume I can get the gradient. And we'll talk about the variational formulation and the Krotov algorithm and GRAPE, which is, one can think of it as a piecewise constant view of the Krotov method. And then we'll go on to other ways of doing gradient-based algorithms. So, what's the idea of gradient-based? So it's fairly simple. You start somewhere and you follow the gradient until you reach the minimum or the maximum. The good thing about it, of course, is that it's fast, and it can handle very large parameter spaces. So 1,000 parameters are not a problem for gradient-based optimizations. The downside is that you must be able to compute the gradient of the goal function with respect to the control parameters, right? You need to know whether I need to move the amplitude a bit up or a bit down and how much. Often, if I'm looking at the variation formulation of optimal control, then this is based on the calculus of variations, which personally I find non-trivial from a mathematical perspective. And that means you need to work a bit hard, which I don't like to do if possible. Okay, so let's go through the derivation and what's the idea. We look at the state transfer problem, okay, as opposed to a gate generation problem, but there really is no difference. So we start with our goal function, right? So we want our state at the final time t to have the maximum overlap with our goal state. But we want to make sure that the evolution of psi of t follows the Schrödinger equation. Now, because we are in the calculus of variations, and something like the Schrödinger equation can be thought of as a constraint, then we rewrite it in a way where everything is on one side and you have 0 on the other. Okay? So this is just the Schrödinger equation, but I moved everything onto one side. Now I want to enforce this constraint. So the way I do that is with the Lagrange multiplier Chi, right? So now this becomes Chi is my Lagrange multiplier. The Schrödinger equation is now a constraint. But of course, I need this constraint to be effective at every point in time. So I need to integrate from time 0 to the final time over my constraint. So now the functional which I wish to maximize in this instance, right, is J tilde. Now, what I didn't write here, just so this page is not full of expressions, is that you need to set the initial state as well as a constraint, right? Because I know that psi at time 0 is equal to whatever the initial state of the system. Now, if you look at what we have here in the functional, then you see that, yes, psi is a quantum state moving forward in time, and Chi is acting as the Lagrange multiplier. But one can also look at it as Chi being a quantum state moving backwards in time, and psi serving as its Lagrange multiplier, making sure that Chi keeps to the time-reversed Schrödinger equation. So what we have here is we have two states, one moving forward in time and one moving backwards in time. Okay, so these variational methods are gradient-based because I'll go back just a minute. Okay, I'll go back here. I have h of t here, so of course I can take this functional. I can take its functional derivative with respect to c of t, or if c of t is parameterized with respect to the parameters governing c of t. And then I have the gradient of the functional, right? So I want to maximize this functional, and I know how to compute the gradient, right, with the functional derivatives, and therefore I can do a gradient-based optimization to reach the maximum. Okay. Now, this idea is also known as the Pontryagin maximum principle. Kind of old Russian mathematician idea. This is also Mr. Krotov, which kind of took this idea to optimal control in general. It requires propagation backwards in time, right? Because we have Chi that is propagating backward in time. Personally, I find this a bit mathematically non-trivial. It is, however, extremely flexible because C of t can be anything you like, any basis you can imagine. We can parameterize C of t using Gaussians, using Fourier bases, flat-top Gaussians, anything you like. And if you're smart about it, you can even reach monotonic convergence, meaning you can be assured that every step of your optimization actually improves things. And for more details about that, you can ask Christiane. Okay. Now, in the context of NMR, we have the advantage that our control electronics are much faster than the typical timescale of the dynamics of the system. Meaning that if I look at the world in the timescale of the system, I'm capable of producing square pulses. Now, this is not true, for example, for superconducting qubits, right? But it is very much true for NMR. And in that case, what we can do is we can parameterize our pulse as a piecewise constant function, right? And then what we want to do is, at each step of the gradient-based optimization, to compute whether we want to increase or decrease the amplitude of each piece, and by how much. And if you make this mathematically explicit, what you get is known as the GRAPE method, right? That is kind of invented and championed by Stefan Glaser, who is with us on the call. It is extremely, extremely fast. It works very well for NMR because we can generate what is effectively square pulses. However, in systems where the timescales are different, so that we are effectively very bandwidth limited in our controls, there is an issue that piecewise constant is not a good approximation for bandwidth limited controls. And experimentally, it's also extremely hard to calibrate, to do the gradient-free optimization for, let's say, thousands of parameters, which are the amplitudes of the control pulses. And to kind of emphasize how much this is an issue, this is, for example, dynamics of a system where you have a nice smooth Fourier control field. The energy scale of the system is set to 1. And what you can see at the bottom plot is how many pieces of piecewise constant do I need to get the correct fidelity at time 20. And what you can see that if, for example, I want a 10⁻⁵ fidelity accuracy in my propagation, I need more than 10,000 pieces. Okay, so I'm not saying that piecewise constant propagation is bad. It actually may be efficient in certain cases, but one should be very aware that often you need to go well above 1,000 pieces to get accurate propagation. And if you don't, you're essentially doing optimization over a skewed simulation, and then it's a garbage in, garbage out situation. So be careful.
Shai, maybe
yes.
just a short comment. It's true that the original GRAPE was proposed for this piecewise constant functions for NMR. But in the meantime, there have been many papers. I think one of the first was by Tom Skinner, probably 6 or 8 years ago. So by using the chain rule, you can easily apply the GRAPE approach also to parameterized functions, either Fourier transform or Gaussians or whatever. So I wouldn't mix up or wouldn't marry GRAPE with piecewise constant. So I think it's two different concepts, but GRAPE is much more general than piecewise constant. Just a short.
Right. So I of course agree, and I'm getting to Skinner somewhere in the somewhere down the line in the talk. But just kind of to elaborate on the comment, the idea is that if you have a general parameterization of your function, and you can do the propagation with piecewise constant, you compute the gradient for this piecewise constant propagation, and then essentially use a Jacobian that takes you from the arbitrary continuous analytical parameterization to the piecewise constant representation and back. Okay, but of course this is a point worth making. Okay, so what do I want from an optimal control method in general? Well, I wanted to be able to do state transfers and gate generation and unitary and Nienblad and non-Markovian evolution, etc. I want it to be flexible. So it's important that I'm able to use any control ansatz and apply any constraints. Why? Because we need to limit the pulses that we get out of the optimal control package to something we know can be implemented in the experiment, right? This is not a theoretical tool. This is a very practical tool. So, for example, if I know that I have an arbitrary waveform generator that has 1.2 gigasamples per second and a 300 megahertz a low-pass filter built into the waveform generator, then I am very limited in the bandwidth of the controls I can use. So we must make sure that we are flexible enough to remain within what is experimentally feasible. Another point is that ideally I want to be able to do multi-goal optimization. Sorry. What do I mean? So, for example, of course, I want my optimal control pulse to generate the desired gate, but I also want it to be fast, or I also want it to use the minimal energy, or I also want it to avoid certain areas of the Hilbert space because I know that certain states are dissipative, right? And if I accidentally go to these areas of the Hilbert space during my evolution, then I'm likely to dissipate away. So I may want to impose all kinds of constraints and multiple goals. And I want it to be quick, and I want it to be accurate. Okay. So so first we have the constraints from the experiment, and these are given, right? So it's power constraints, bandwidth constraints, timing constraints, etc. I need to be able to support non-linear filters because often the control pulse I generate and the control pulse that actually gets to the system are different because lines have attenuation. Every single parameter in the optimization is constrained, right? Power, timing, etc. An example is, as I described before, is an arbitrary waveform generator with a low-pass filter, then adding an IQ mixer, so you have the AW generating the envelope, and you have a fast oscillating carrier within this envelope, and the IQ mixer is what adds the carrier in. Now I can choose a control ansatz, one so that my pulses look simple and I have a hope of understanding why they work. So this may be Fourier or error function or hand window or Gaussian or piecewise constant or anything else. For the purposes of calibration, we really would like to have simple pulses because calibration is a gradient-free optimization. As such, it is limited in the number of parameters it can concurrently optimize. And therefore, if we have a pulse that has a simple representation, we'll have a much easier time at the calibration stage. Okay, and now we'll talk about GOAT. So if we are free to choose our ansatz and we choose it wisely, that will mean that we'll have simple pulses and the gradient-free search for the calibration will work well. So that was the primary motivation. Also, we'd like to keep it simple if possible. Okay. So GOAT, which I'll present now, allows simple pulses, i.e. arbitrary ansatz. It's gradient-based, it's fast, it's flexible. I'll show how to do various cool things with it. It's mathematically simple. There's no adjoint state, there's no backpropagation, and it's only one slide to derive it. So that's also nice. Okay. So let's go back to the original statement of the problem. We have the Hamiltonian, drift, and control fields. The unitary is the time-ordered integral over essentially the Schrödinger equation, and a goal function is the overlap between the unitary I actually do and the unitary I wish to do. And we want to find alpha such that G of alpha is minimal. So the idea is simply compute the gradient and follow it. Okay. So if this is my goal function, computing the gradient is rather easy. Left as an exercise to the reader, but after like 10, 20 minutes, you'll convince yourself this is indeed the gradient. But then we come to the tricky question of what is the gradient of U with respect to alpha, right? Now, the issue is that the only thing we know about U is its equation of motion, right? So U essentially follows the Schrödinger equation of motion, right? By the way, one way you can think of this, and for some reason people don't often do. You can think of the unitary as just a collection of columns. Each column is a state. At time 0, U is the identity, right? We haven't done anything. The state hasn't changed. And the columns of U are just a very simple basis for the space of states, right? We have a column with 1 at location 1. We have a column with 1 at location 2. We have a column with 1 at location 3. So that's a very simple basis with which to represent quantum states. And then each of these basis vectors propagates according to Schrödinger. Okay, so this is the equation of motion for U. But how do we get from this? How do we get the gradient of U? Well, one thing we can do easily is just take this equation of motion and derive it with respect to alpha. So because H is dependent on alpha, therefore U is dependent on alpha, therefore we have to derive each of these independently. So we have the derivative of H with respect to alpha, which is trivial, but also we have the gradient of U with respect to alpha, which is non-trivial. And the object we have here on the left, which is the gradient with respect to alpha of the time derivative of U, that's a weird object and it's not exactly clear what to do with it. Luckily, we are in physics and all functions are analytic and we can switch orders of the derivatives. And when we do that, this suddenly makes sense. We have two equations of motion here. I can also write it this way, perhaps clearer for some. So we have two equations of motion here. One equation of motion for U, one equation of motion of the gradient of U. So just like you propagate U in time, you can propagate this equation of motion in time. Of course, it is coupled to the primary equation of motion, and that's it. You just take this object, you propagate it forward in time using Runge-Kutta, piecewise constant, or whatever form of propagation you fancy. And at the end result, what you have is you have the gradient of U with respect to alpha, which is what we need in order to compute our gradient. One thing I want to point out, just in case it's not clear, because alpha is a vector, when it says the gradient of U with respect to alpha, that essentially means a lot of gradients of U, right? Because we need one for each parameter. So it's not two equations of motion, but it's the dimension of alpha plus 1. But you don't really care because the computer just propagates them all together. And that's it. That's GOAT, because then we know how to compute the gradient. And then you can do all kinds of fun things with it. For example, we talked about unitary gate, and if you look at a single column of U, this is essentially a state transfer problem. If you want to look at the Lindblad equation, then you just take the Lindblad equation of motion, you derive this with respect to alpha, and everything else proceeds as before. If you want to do Lindblad, doing a general density matrix propagation and the superoperator more than that is extremely heavy numerically. Christiane has this wonderful paper about the 3 magic states. At least that's how I remember. I heard her call it in one of the talks, and this reduces the numerical cost of evaluating something that is similar to the fidelity very significantly. One can also do other things. For example, let's say I'm not really interested in a specific 2-qubit gate, but instead I only care about a gate that will entangle my qubits. So I'm essentially looking for the best way up to some local rotations before and after the 2-qubit gate, right? If I'm thinking of quantum computation generally, one can think of it as single qubit gates and then a 2-qubit gate, single 2-qubit gates, and then a 2-qubit gate. Because all the single qubit gates on the same qubit can be essentially mashed together into one rotation. So what you can do in the GOAT way of phrasing things is change my unitary to include pre and post rotations, right? The pre-rotations are signified by θ1 and θ2, and the post-rotations by θ3 and θ4, and you just change a little bit the chain rule used to derive GOAT, and then GOAT will find the best entangler for this specific system and tell you what pre- and post-rotations are needed to, for example, change it into the CNOT or ISWAP or whatever 2-qubit gate you desired. Okay. Now, how do we do ODE propagation? Because for almost for every quantum optimal control method, we need to propagate the state, right? So generally speaking, one can think of two easy ways, and there are a lot of more sophisticated ways. So in the case of fully coherent propagation, you can think of doing piecewise constant, or you can do Runge-Kutta. Okay? Now, if you're Hamiltonian, rephrase. Okay. Runge-Kutta can respond very well to changes in the Hamiltonian. So it will take a lot of steps, but if the Hamiltonian changes rapidly, right, that means that the bandwidth of the control is on the scale of the energy of the system, then Runge-Kutta will respond better. But if you have a situation where your controls is comparatively slow to the system timescale, then piecewise constant will perform better. And for example, in superconducting qubits, this is often the case, where our control field is moving rather slowly, whereas the energy scale of the system is much higher. There is also a very nice work, again, from Christiane's group about iterative time ordering propagator, but I don't have any personal experience with it, so I cannot comment how easy or how fast it is. But there's also a lot of other work on how to do the ODE propagation. Now, in terms of if your system is almost coherent, okay, then and with quantum gates, this is often the situation. You usually don't want to do the full density matrix propagation. It's very wasteful. So one can think of it as quantum jumps. The idea is that you do a coherent propagation up to some random point in time, do one of the Lindblad operators, be it the dissipation or dephasing or whatever, and then continue with the coherent propagation. You do this several times with having this quantum jump, this incoherent action happening at different points along the process. But even if you do this ODE propagation multiple times with the quantum jumps at different locations in time, it is still much, much cheaper than doing the full density matrix propagation. In case of non-Markovian effects, one usually defines not only the system and environment, but something that I like to call DMZ. It's the buffer, the demilitarized zone, as you have between North and South Korea, which is essentially you take some of the environment and add it to the simulation of the system. And there is work from the Martin Plenier group in Ulm about how to simulate various categories of non-Markovian environments and how many spins you need to add to the system description to get the non-Markovian simulation accurate to a certain degree. And then if you have the full Markovian, then if the Lindblad operators are sparse, which they usually are, then it's better to use the Lindblad-Kovakovsky-Maxwell equation than use super operators, at least from my experience in terms of numerics. Okay, now, As we mentioned previously, when we're doing quantum optimal control for experiments, everything is constrained. So we need to find a way to impose these constraints within the optimal control. And there is a trick which is rather trivial that I found to be very useful, which is the following. Let's say my control field is a single Gaussian pulse, and I want to constrain the amplitude A. So instead of having A as the parameter, I replace A with this scale sine function, or cosine. Okay? So now the parameter I optimize is not the amplitude, but this angle that goes into the sine function. But the expressions here in the parentheses are now constrained. And in for example in the GOAT package, this is what we do for every parameter. Okay, so all our optimization parameters are order 1 and unbounded from this perspective of the search function. But in terms of physics, everything is bounded and at the right scales. Also, this really helps a lot for almost all search functions you can think of, CMAS, LBFGS, etc., etc. They like it when all the parameters are order 1, so make sure you rescale your parameters. It makes life a lot easier. Now, let's say I have bandwidth constraints at the beginning and the end of the pulse, meaning I want my pulse to start at 0 and end at 0. What do? Well, we define a window function that's 0 at the beginning and end, and 1 in the middle, essentially a flat-top Gaussian, and we multiply our control function with this. And when you use that approach, you can see here, for example, we use the Fourier basis, where the frequencies are constrained, and then we use the window function to make sure we start smoothly at 0, then we have the full amplitude, and we end back at 0. And in the context of GOAT, this just goes into the derivative, and you're done. Another example, I'll do this one quickly. Let's say we have transfer functions. So we have an attenuation on the line. Okay? So you have a voltage you put into the line, which is V in, and then the line does things to the signal, and you have a V out. Now, your Hamiltonian is not dependent on the V in, which is, let's say, what comes out of the waveform generator, but on the V out, which is what you have at the experiment. How would I integrate that into optimal control? Well, if you go back to your undergraduate studies, a low-pass filter can be implemented with an RC circuit, so of a resistor and a capacitor. The V in is here, V out is here. Okay? And if I want to describe the internal state of this circuit, I need two state parameters. They can be, for example, the current in this loop and the charge on the capacitor. These are the equations of motion for this circuit. And if you don't remember those, find an undergrad. You'll know them well. All I need to do now is couple that to my Schrödinger equation, right? And the way this is coupled to that is through here, right? Because V out is just dependent on the charge on the capacitor. And then I do what I always do with GOAT, which is I derive everything with respect to alpha, switch the orders, so I have this equations of motion for the gradient, and then I just propagate as normal. You can also see something very similar done in this paper below. Okay. Another point related to optimal control, which is robustness. So the accuracy with which we control our quantum system is always limited. And things change over time. And the way we respond to the changes in the context of optimal control depends very much on the time scale of the changes. What do I mean? So if the changes are much, much slower than the time scale of my experiment, then what we have is essentially characterization gaps, meaning either the model is too simplified, or we haven't measured everything that we should, or there's some fabrication variability or something like that. The solution to that is to regularly recalibrate your experiment, your model, and then adjust the optimal control pulses accordingly. Now, if the time scale is slow, meaning, but it's not, it's no, but it's not static, meaning it's on the time scale of the operations in the experiment, then you can do one of two tricks. You can either do dynamic decoupling, spin echo being the kind of canonical example, right? Or you can require, for example, that the second order rephrase, that the gradient of the fidelity with respect to the parameters that drift, that the gradient will be zero, meaning that the system will be relatively insensitive to the changes in the parameters that drift. Okay, and what we see here that often, this, for example, is a measurement of the noise in a superconducting qubit experiment. And what one can see is that usually we have a 1 over f noise, meaning we usually have noise at all time scales, right? So we have very, very slow noise, which we should really just resolve by recharacterizing the system and rederiving the pulses. Just, recalibrate the system every morning and readjust your pulses. Then the middle stuff we do with dynamic decoupling or more sophisticated pulses. And then the really fast noise, right? One which is faster than our control time scale, then the only way I am aware to do that is to essentially do an ensemble optimization. Meaning that instead of optimizing over one propagation of the system, you replace one propagation with, let's say, 50 propagations with different manifestations of the noise. You just add noise in your simulation, and you do the optimization over multiple manifestations of the noise. Of course, this is heavy numerically, which means that if you can do it with GPUs and do it in parallel, this is extremely helpful. Another point is what is known generally as regularization, and in our community more often known as penalty terms, which is we want to force the optimal solution to go in a certain direction. So, one example is forbidden subspaces. Let's say I have a subspace which I want to make sure I don't visit. For example, if you're looking at a trapped ion system, right, then usually my 0 and 1 are two hyperfine levels that are kind of, have a reasonable energy separation between them. But because there is no direct transition allowed, one does a gamma system by bouncing it off a very, very high level. But the levels up there are highly dissipative. So you want to make sure that you don't occupy these highly dissipative levels at any point during the dynamics. So what you do is you define a projector P into the forbidden subspace, right? And you define a penalty term Q that is proportional to how much I am occupying this forbidden subspace. and you add that as a secondary goal to your optimization. So I want my fidelity to be good, but I also want my penalty term to be low. Another example is, let's say I want sparse controls, meaning I want to have as few Gaussian pulses as possible. So I will define a penalty term, right? That is, let's say, the square root of the amplitude. In this case, what you'll get is that the optimization will try to concentrate power in as few pulses as possible. So that's another penalty term one can add to the goal function. One can also require the drive to be geometric, but I'll skip that. But this is the penalty term that's appropriate in case you want to do that. And then, if I'm doing a multi-goal optimization, what we can do is define a landscape for, if you look, the x-axis is the log of the g, of the infidelity, right? So on the right-hand side, this is really bad. We have very high infidelity. And let's say 10 to the minus 4 infidelity is very nice. And on the y-axis, you have the penalty term, okay? And you define a combination function that takes both the log of the infidelity and the log of the penalty and combines them into a single goal for which you optimize. And if you set this system up correctly, what you'll get is that it'll try to keep both the fidelity and the penalty low and drive the system into the region where everything is good. Okay? So this is how you combine penalty terms into your optimal control. Okay, now a few results. This is just kind of to show you what can be done with optimal control. So we're looking here at the cross-resonance gate used by IBM in the IBM Quantum Experience and that sort of devices. So what you have is you have two transpons coupled by a resonator. And the idea is rather simple. You oscillate one qubit at the resonance frequency of the other, and then you generate entanglement. Because, of course, the resonance frequency is dependent on the state of the qubits, etc., etc. So what IBM has right now are 2-qubit gates that have 992 fidelity, and they require 160 nanoseconds. The pulses used are really rather simple. It's just 3 or 4 flat-top Gaussians. Now, what we showed by running optimal control of this system is that we can take the time down from 160 nanoseconds all the way down to 15 nanoseconds. If you allow highly complex pulses and you allow there are various ways of doing it, with one carrier driving the qubit, or 2 carriers driving one qubit, or each qubit having its own carrier. You can play around with it. But basically, the idea is that if you allow more complex pulses, you can drive the system a lot faster and at much higher fidelities. Now, of course, driving the system faster is hugely beneficial because we're essentially fighting against Markov. And Markov is the big enemy, and the faster you do it, the better. Another example is the flux-tunable coupler, where the idea here is that you have 2 fixed frequency qubits, Q1 and Q2, and you have in the middle a qubit that is flux-tunable that can be moved in and out of resonance with the qubits around. But if it's completely out of resonance, then the qubits are essentially decoupled from each other. Now, in the context of quantum computing, this is very important because if we have 100 qubits, unless we find a way to decouple them in some way, either shifting their frequency or using this tunable coupler, you'll end up with terrible frequency crowding. because you'll have multiple qubits at the same frequencies, and they'll start to resonate with each other. So in the context of this problem, this is the Hamiltonian describing the system. And what I want to kind of emphasize to you is what we actually control. Okay? So what we actually control is the flux going through this circle here. Okay? This flux has a bias, it has a carrier, and it has an envelope. Now, once you determine this flux determines the resonance frequency of the tunable coupler, and this resonance frequency goes in here to the Hamiltonian. So unlike the original situation we described where we just had a prefactor for Hamiltonian term, here this is buried quite a bit in terms of the functional dependence. However, at the end of the day, this is just a chain rule, right? This is undergraduate level chain rule. So if you know how to compute the gradient of delta with respect to alpha, then of course the gradient of H with respect to alpha becomes trivial, and you go back to the GOAT equations of motion and everything is simple. And this is an example of an optimization we did. This is the final pulse shape you see at the bottom. What you see, by the way, at the top is how the pulse looks before we impose the window function. So you can see we don't start at 0 and we don't end at 0. But then we impose the window function, and we also impose a y constraint. So you can see that there's a limit to how much flux we allow. And this is when you add both the bias and the carrier. So this is how it looks. And if you put that into the system, you essentially get what up to Markovian effects is a perfect gate. I'll skip that for time. How much time do we have? Does anybody know?
How much more time do you need, Shai?
You know, I can keep talking until tomorrow, but...
well, I think we want some time for students to ask questions, but from my point of view, another 5 to 10 minutes would be okay.
Okay. Okay, so there is, let's say, a few points I want to touch. One is how important it is to have a very accurate model of the system. In the context, for example, of quantum computation, we're looking to get gates with 10⁻⁴ in fidelity. Now, the possibility of getting gates with 10⁻⁴ in fidelity when your model doesn't have a commensurate accuracy is very low. And as an example here, you can see a paper by Lucas and Frank from 2017, where they showed that even very, I'll rephrase it this way. We aren't explicitly driving the flux of either Q1 or Q2 in this flux tunable coupler setup. So often one assumes that their frequencies are constant. And if you actually look at how the flux of Q1 and Q2 affects their frequency, you can see just from the values of the y-axis that if the flux is not too great, you're really in a fairly flat region. So one can naively think that I can model the system with fixed frequency Q1 and Q2. But actually, this is not the case. Because if you want 10⁻⁴ fidelity, even this very slight dependence on flux in the qubit frequencies is enough to generate errors of this order. So as far as I know, for example, I'm currently focused very much on quantum computation, so I'm aware of what's going on there. And I can tell you that with the exception of Google, I don't believe anybody has a model of the system that is detailed enough so that they can predict the fidelity of their gates from simulation. And if you don't have an accurate enough model, it's very hard to determine your error budget. Meaning, if you want to take your infidelity and break it down into various reasons, what is a coherent error, what is non-Markovian effects, which I don't compensate for, what are true Markovian effects, if you don't have a highly accurate model, you don't really understand what's going on. So this is something I really want to emphasize. It's quite important. This is kind of just showing. This is we're generating. This is a project we're working on right now. This is generating entangled states in trapped ions on a sub-microsecond timescale. And this is a joint optimization because we have some penalty terms related to dissipative states. A few more very quick points. Controllability. Controllability is an extremely important issue in the theory of optimal control. And it essentially asks, can we implement any gate we wish? Can we implement a specific gate? These are, of course, two separate questions. Now, for coherent dynamics, this is rather simple, and it's essentially answered by the closure of my Hamiltonians. So I'm looking at my Hamiltonians, including the drift and the controls, and their commutators and the commutators of their commutators, etc. And if this entire series, at the end of the day, provides a basis for the entire Hilbert space, then not Hilbert space, but the space of Hamiltonians, then I'm good. Why? Because if you think of when you merge e to the a and e to the b, right? This equals to e to the c, where c is described by the Baker-Campbell-Hausdorff series that is composed of these commutators and commutators of commutators, etc. So if these describe all possible Hamiltonians, then by choosing the weights correctly and the time dependence correctly, I can get any Hamiltonian I want. And this is what I was talking about. Now, as far as I know, for open systems, this is not a fully resolved question, and research is ongoing. Another point I wish to raise is local traps. The question is basically, how does the topography of the optimization landscape look? Is there an easy way to get to the local minima? And this is advocated, by the way, by Herschel Rabitz of Princeton. Or are there a lot of local minima, and depending on when you start, you might end up in this, which is not a true global minima, or you may actually go to the global minima, etc., etc. And in this case, optimal control is hard. And this issue, and this point of view is advocated by David Tanner of Weizmann. And I think the discussion is going on, but in the context of practical quantum optimal control, we know that all our parameters are constrained. And in case when you add constraints to the system, then everybody agrees there are local traps. Right? So you will find often when you run optimal control that you run into local traps. You don't get to the fidelity you want. For example, it's been my experience that if you use a Fourier basis, and if you start with frequencies that are an order of magnitude away from the frequencies you actually need, then this will not converge, and you will get very bad results. going all the way back to flying our probe to Saturn, this is exactly the problem that if you try a trajectory that's very far away from Jupiter, you're not seeing a gradient of this gravity assist as you approach Jupiter. You must be in the neighborhood, right? This is the standard quantum resonance situation, right? If I have a Lorentzian describing a resonance, but I am 10 sigma away from the resonance frequency, then all I see is a flat zero. So there are absolutely, definitely local traps in practical optimal control. And there isn't a magic bullet to handling them. The trivial approach, of course, is just start at many different points and try. There are algorithms that try to do a better job in this, which is stuff like simulated annealing and tunneling and genetic algorithms, etc., etc. You can even start with something like CMAES that starts with a cloud of points that somehow samples a lot of the space and stop it at some point where it's more or less in the neighborhood of something good, and then switch over to a gradient-based search. But there is no magic bullet. Another point we need to consider are forbidden subspaces. I touched upon this earlier. So this is, for example, the standard way of doing gates in trapped ions. So you have the 0 and 1 states that are fairly close, but there's no direct transition. The way we do it is we do a transition through a virtual level, but it's quite close to level 2, which is highly dissipative, and you want to make sure you don't go there. Another issue is that for a lot of systems, we don't have very good characterization of the entire Hilbert space. We know how the system looks in a subset of the Hilbert space, but we don't really understand what's going on generally. And therefore, you want to limit your optimization to stay within this Hilbert space. Another point is the do not disturb issue. For example, what you see here is a Google chip. These are the Xmon qubits, called because they look like X's. And let's say I want to drive this qubit to a single qubit gate, but I want to make sure I don't change the state of any of the neighboring qubits. So essentially what I want to do is to make sure that I don't go into certain areas of the total Hilbert space of the system, that I stay only within my little neck of the woods. Right. There's also a numeric reason that's extremely important, which is the Hilbert space cutoff. Often in our systems, we'll have harmonic oscillators, or let's say even the transmon qubit has quite a few levels in it. But for numerical reasons, we don't simulate the entire system, right? We have to cut it off. We don't have infinite memory. So what we do is we just cut off, let's say, these levels. So we simulate levels 0, 1, and 2. But doing that is extremely problematic because now this is no longer a harmonic oscillator. This is a 3-level system, and its behavior is very different than an harmonic oscillator. So how do you compensate? You simulate level 2, but you also require that it remains unoccupied. So you essentially have a buffer level, or sometimes 2, before the cutoff, and you impose a penalty term, making sure that these remain empty. Okay? And by doing that, you can be sure that the result of the optimization is valid even though you cut off the Hilbert space. Another approach is to do a very carefully designed space for pulses, but we won't touch upon that. Now I want to skip a bit because we don't have a lot of time. Okay, let's talk a little bit about the quantum speed limit. So there is a question of how fast can we rotate from one state to another, meaning go from an initial state to some desired state. And if you think about the speed limit for gates, this is essentially the same, but for multiple concurrent rotations. So for time-independent systems, we know there are limits to how fast you can go. As far as I understand it, for open systems, this is an open question. What we can say, however, generally, is that if the system... Sorry? Okay. If the system is controllable when you take out the drift Hamiltonian, then there is no speed limit. Why is that? Because then I can, with my controls, eliminate the drift, right? Because I have full controllability without the drift. So my controls can generate minus H0, and then I just multiply all my fields times a million, and I go as fast as I like. Also, we know that if you cannot control your Lindblad operators, then there are speed limits. Okay. Okay, this is coming up at the wrong order, so we'll do it like this. This is a simulation we did for a gate we optimized. And what a situation you often see is the following. In real systems, we have dissipation. We can't take as long as we want. Okay? So if you go too slow, Lindblad starts killing your fidelity. However, if you go too fast, then you start becoming very spectrally wide. You start resonating all kinds of transitions in the system you didn't want to. You need to increase the complexity of your poles to compensate, and at some point you can't win. So often in real systems, there's actually an optimal speed for best fidelity. Because we lose something if we go very slow, we lose something if we go very fast, so there's a sweet spot in the middle. So that's something to be aware of, and I think I will skip the next point. Okay. So to summarize, optimal control is a very useful tool, and it allows you to increase the performance of your operations, whatever they are, very significantly over naive analysis. Another point to consider is that if you're using highly simplified models so that you can do analytic analysis of the system, right? That means that you're already introducing a significant error by doing these rotating wave approximations or dispersive frames or whatever it is, right? So by using numeric optimal control, you can work with a much more accurate model of the system, one which you cannot analyze analytically, but there's no problems doing numerics over it, and you can get very good performance. However, the problem is that quantum optimal control, at least open loop quantum optimal control, is only as good as the model, right? If we have an inaccurate model, the pulses won't be very good. So the solution, and that's where the outlook comes in, is that we're looking, kind of looking forward in terms of research. It would be very interesting to find the quantum optimal control equivalent for system characterization, meaning have automatic or semi-automatic methods to characterize the system. Now, in certain limited situations, there are ways of doing that. For example, there is something called gate set tomography, which will give you the super operator for a 2-qubit gate, but requires you to do several thousands of measurements and then several hours of processing in the computer. So the methods we have right now to generate a model for a quantum, generate a highly accurate model for a quantum systems aren't nearly as good as we would like them to be. And this is a challenge that at least my work is focused on in the near future. And thank you very much. And if you have any questions, please ask.
Okay, thank you, Shai, for this overview. I think you touched upon many things that eventually will need more thorough discussion, but it was a very nice start, and I encourage all students to not be shy, but ask questions.
And also, by the way, I'll just do it right now. My email is simply shaimachnes@gmail.com. You have it on the screen now. So if you have questions later on, just feel free to email me. I'll gladly answer.
Hi, I have a question.
Yes.
Yes, I think that was on slide 17. You did mention it, but maybe I missed the point. This was about a window function that would also control the parameter C.
Where did we do the window function? Here?
Yes.
Okay.
Could you repeat that again? Like how?
Okay. All right. So let's go back for a second to the phrasing of the optimal control problem, right? So we have the goal function, we have the unitary, we have the Hamiltonian, okay?
Mm-hmm.
At the end of the day, what we need is the gradient of the goal with respect to the control parameters, and then you can start following the gradient to the minimum. Now, the control functions appear here. Right? So these would be the amplitude of my control fields, etc. Now, what happens if I want to force my control fields to start at 0 and end at 0? One can think of several ways of doing it, but at least one of the ways is the following. I multiply my control fields with a time-dependent window function. It's essentially a flat-top Gaussian that's 0 at the boundaries and 1 in the middle, and a smooth transition. Okay? So now my control fields are guaranteed to start at 0 and at 0.
Okay.
This then changes the way the Hamiltonian looks here, and essentially you have a multiplicative factor for the gradient of h with respect to alpha. Right? You add omega, add a window of t in there.
Okay, thank you. Yeah.
All right. Any further questions?
Well, I have another one, but I don't know if someone else is waiting for a question, and I can wait.
I would have a quick one. So Stefan Philipp speaking. Hi, Shai.
Yes.
You talked about the two problems, that there is the local traps problem and there is the not knowing about the system Hamiltonian problem. Would I be able to distinguish between them if the fidelity is my final metric, basically? So all would end up in having not the best fidelity that I would like to have. Can I distinguish whether my system is not well described or whether I'm ended up in a local trap? Do I know what to improve on?
Okay, not from optimal control, but you can distinguish the two. If I have a good model, a good model is one that predicts the fidelities of the gates, right? So so we can check whether our model of the system is good just by seeing if we reproduce the fidelities of the gates we're seeing. It doesn't have to be very good gates. You need to reproduce the fidelity whether the gates are good or bad.
Okay.
So this way you can tell whether your model is good. And then if you're willing to invest enough silicon into the optimal control problem, there are algorithms that are fairly robust to getting out of local minima. And then you can kind of get around that problem just by, throwing a rack of GPUs at it.
Okay.
And I'm actually, we will see each other at next week at Bad Honnef, and my poster actually deals with exactly this issue.
Okay, so I think I'll drop by at your poster then.
Anybody else? There was another question you had?
Yes. So my other question was, when we talk about the local traps, I'm aware it happens in the gradient-based, but in the gradient-based optimization algorithms. Is it also true for like the non-gradient-based? Or
Yes, okay. Because the local traps are a feature of the landscape, not how you search it.
Okay.
So if there are no local traps, then almost no matter what you do, you'll get to this one global minima. If you have local traps, then depending on when you start and how you walk and how many walkers you have on the landscape and, you may end up in one of the local minima, which is not the global minimum.
Okay. Since in our group, at least I've worked with more the gradient-based, so I was not sure if that happens also for the non-gradient-based or how to understand.
Yes. Yeah. So there is gradient-based methods are very good at finding the let's say the local minimum. Okay. However, if they start in an unfortunate place, the minima they go to may not be good enough, right? Because to be honest, we're not really searching for the global minima, right? So if we're talking about gate fidelities, if we get to 4 nines or 5 nines, we're happy. We don't really care if the global minima is 76 nines, right? We don't have enough bits in our waveform generators for this anyway. So I think from a practical perspective, we're not really looking for the global minima anyway. We're looking for a good enough minima.
Okay.
And there are, I'll say this, generally speaking, gradient-free methods are better at not getting stuck at local minima, but they are very bad at converging to the minima, even if they are in the neighborhood. So there is work about switching from gradient-free to gradient-based optimizations at certain points. So you try to apply some criteria to identify whether you are in some local basin, right? And if you are, then you switch over to a gradient-based method. And if you email me, I can find you the reference.
Okay.
There is some work on that, but I know with certainty this is very much an open question in computer science. There is no canonical answer.
Mm-hmm.
This is just a really hard problem, period.
All right. Yeah. Thanks a lot.
No problem.
Shai, I have a question as well. Like as you said, if you're stuck in a local minima, you can shift from any algorithm to the gradient-based algorithm to get to a global minima. But I mean, so we have to translate like that problem into a gradient-based problem as well. Like, is there any compatibility in the algorithms like that would be transferred to, or like any algorithm could be transferable to the gradient-based?
So the question with the gradient based is, do you know how to compute the gradient?
Okay.
So the variational methods suggest one way of doing that. GOAT suggests another way of doing that. But overall, the question is, can you efficiently compute the gradient? Because if you can't compute the gradient efficiently, if the best thing you know how to do is finite differences, then it's not worth the effort. Because if you're doing gradient via finite differences, you essentially evaluate multiple points to compute the gradient, and then you take a step with the search. But good gradient-free algorithms learn from each point. So you're essentially, let's say I have 50 parameters, okay? So to do finite differences, you need to compute, let's say, 1 point plus 50 other points around it, right, in the various directions. And then you take the finite differences. So you evaluated 51 points, and then you take a step, then you learn something. Whereas if you do gradient-free methods, like good ones, then after each point you evaluate, they already learn something, and they're a bit smarter about choosing the next point. Now, this breaks if you can evaluate the gradient quickly, right? If the cost of evaluating the gradient is, let's say, an order of magnitude less than finite differences, then it's worth the effort.
Okay. Thank you.
Actually, I also have a comment with respect to the finite difference approach. I mean, I completely agree what you said. If one uses kind of a simple-minded finite difference approach, and we used the same arguments like 20 years ago, but some years ago we had a paper together with Sonja Schirmer, and Ilya Kuprov was, I think, also one of the authors. And there we showed that by using kind of clever finite difference methods, one can be actually as efficient as using this forward-backward propagation. Basically, you also, rather than 2 propagations, you do 3 propagations, but so you are very efficient can be very efficient calculating gradients using finite difference. It's just not doing the simple-minded approach where you evaluate the functions at different points and recalculate everything as if you have no information about the system.
Okay, I'm unfamiliar with the work, but I'll change that.
Are there any further questions or comments?
Yes, I would like to make a quick question regarding parallelization in different algorithms. Is there any benefit in using gradient-based or non-gradient-based algorithms regarding parallelization, which is an important thing if we're talking about the time that we are planning to run our simulation?
Yes, so you can parallelize at many different levels. So starting with the underlying propagation, okay? If you do a matrix exponentiation today in NumPy or MATLAB, etc., everybody uses the LAPACK library, which itself is parallelized. So the matrix exponentiations will be parallelized. If you're doing propagation via piecewise constant and then either using it directly or folding it into some general analytic parametrization via a Jacobian, then you can parallelize each of the time steps. Okay, so that's another avenue of parallelization. If you're talking about gradient-free optimizations, then algorithms such as CMAES can either evaluate one point each time, or it can evaluate multiple points and then learn. And then each of the evaluations can be a different thread and be parallelized. In the context of GOAT, where you have equation of motion for the gradient, then each one of those plus the primary can run separately. So one can parallelize this as well. So there are many avenues for parallelization. To the point where I can say that I think that virtually every method can occupy all CPUs and GPUs you throw at it, if you code it right. So the limitation in parallelization is usually programmer effort, as opposed to something inherent in the method.
Okay, thank you very much.
Any other question or comment? Don't be shy. Okay, now I don't hear anything, and we will make the material of all the QuSCo on air lectures available. Mattia will communicate where exactly, but I think so. You all have the chance to look up the references, and if you have questions, please use Shai's offer to contact him. For today, I think we are done, and we will continue our sessions in person when we all meet in Saarbrücken in the end of February. Okay, so thank you all of you for listening, for asking questions, and see you soon. Talk to you soon. Thank you, Shai.
Bye-bye, everybody.
Bye.